Another important aspect of nuclear chemistry is this concept of half-life. And as you see here, it's the time required for half of the atoms of a radioactive sample to radioactively decay and become stable. And the half-lives of these radioisotopes are measurable and pretty set in stone. They occur at a definitive rate. Some radioisotopes have extremely long half-lives, which is one of the reasons why nuclear chemistry gets a bad rap. All the nuclear radioactive waste we create from power plants right now is going to continue to be radioactive for billions of years. Some radioisotopes have a very, very short half-life, which is good, and for like uses in nuclear medicine. So if you get injected with a radioactive isotope, then it doesn't remain at a high level of radioactivity very long in your body. It's there for the purpose to be scanned or imaged, and then it decays and becomes stable to a safe level. So here you see an example. This is iodine. Iodine 131 has a half-life of 8 days. So every 8 days, half of the radioactive sample becomes stable. So if we start with, let's say, 36 grams here, after 8 days, half has become stable. The other half is still radioactive. After 8 more days, half of what's still radioactive joins the stable club, and we still have half of that is unstable. So technically we have 1/4 now from our original starting amount. And then again, after 8 days, half of what's left joins stable, and half of that is still unstable. So now we're down to 1/8 of our original sample. And then it would keep going 1/16, 1/32, etc. Which, if you've seen an asymptotic curve, which I'll show you here in a minute, then it never reaches zero. There's always a fraction that is still radioactive. So here's a couple little sample problems. Here we have some barium-133 has a half-life of 11 years. And so you can see there, one half-life is 11 years. So it's nothing more challenging to figure out these number of years than to keep adding 11. 22, 33, 44, 55. Each half-life is the same number of years. So as far as the atoms, it's simply a matter of dividing by 2. So if we start with 60,000 radioactive atoms, after one half-life, 30,000 will still be radioactive barium-133. Then we'll drop down to 15,000. Then we'll drop down to 7,500. And then 3,750. And then 1,875. And so on and so forth. And then this question up here asks, determine how much time will pass when 7,500 atoms of barium are still radioactive. That's right here. It would have been 33 years. Pause the video, take a second, and see if you can complete the second sample problem there with technetium-99. Hopefully your chart looks a little something like this. After each half-life, it's 6 hours, so the number of hours increases by 6, and the number of milligrams goes down by half. And you'll notice, as it said there in the question, it's used in nuclear medicine with a half-life of 6 hours. So if you're injected with 4,800 milligrams of technetium-99, a day later, only 300 milligrams is still radioactive in your body. It decays very quickly, becomes very stable, and even though there will still always be a small trace, infinitesimal trace that's still radioactive in your body, it reaches a safe level very quickly. Now the question here says, how much time will pass when 75 milligrams are still radioactive? So that's not on our chart. 150 is the last number here, so one more half-life will take it down to 75. So we'd have to go to 36 hours, because it's 6 hours, one more half-life past 30. And the last little part there, it says because this half-life process is a constant rate, we can perform geological dating. Perhaps you've heard of radiocarbon dating or carbon-14 dating, because that's the most common radioisotope used. The more unstable an isotope is, the shorter its half-life. So carbon, which is present in so much stuff on our planet, it has a longer half-life, but it's really only effective as far as dating objects that are 50,000 years old or younger. Potassium is another element that's found in virtually every living thing on this planet. So if you're trying to identify how old a living fossil is, you could use potassium-40 because it has a half-life of 1.28 billion years, so it can go much further back than carbon. And here's that asymptotic curve I was talking about. So this is the graph for potassium-40. We start time 0, there we have, it's all radioactive. After one half-life, half is radioactive and half has decayed into either argon or calcium, both stable. And then we see, as I mentioned before, now we're at a fourth, an eighth, a 16th, and it'll keep going, but never hit 0. That's the asymptotic curve portion of this topic. So again, stuff that is radioactive will remain radioactive for an extremely long time, but it does eventually get to a level that is quote-unquote safe to us, because as we'll see for the rest of this unit here, we're surrounded by radiation and radioactivity, and we have a tolerance of a certain amount. All right, until later.